Welcome to this video. This video is an example of computing the equivalent resistance of a resistor network. And in this video, we'll compute the equivalent resistance of the resistor network shown here. I try to put together examples that actually have some connection with real live circuits. As best I can tell, this has absolutely no connection with any real live circuit. But it's been put together in such a way that it brings out some of the common misconceptions and mistakes that people make as they're trying to learn how to do this. So, without further ado, let's just start working on this. Basically, what we want to do to find the equivalent resistance of the entire network is to look for series or parallel resistors, and then combine those series or parallel resistors into equivalent resistors, and continue doing that until we're down to just a single resistor. So if we look at this, we find actually two series combinations of resistors. If you look carefully, the 3 ohm and the 1 ohm resistor are in series. You can tell they're in series because any current that goes through the 3 ohm resistor must go through the 1 ohm resistor. There's no other place for that current to go. So these two resistors are in series. We know that the series or the equivalent resistance of two resistors in series is just the sum of their resistances. So we can say that the equivalent resistance of this guy is going to be 4 ohms. Or again, that's the sum of 3 ohms and 1 ohm. So that's one combination that we can make to simplify things. Another combination we can make, which might not be as clearly discernible based on the way the schematic is drawn, is the following. These two 2 ohm resistors here. And I'll ask a question. Let you think about it for a second, and then I'll tell you what I think the answer should be. Are these two resistors in parallel or in series? Okay, so if you want to think more, pause the video. My experience has been that many students will say that these two are in parallel because they've been drawn so that the body of the resistors are parallel to each other. But if you look at it, if you have current coming through this 2 ohm resistor, the only place it can go is through this 2 ohm resistor. So in fact, although these resistors are drawn so that in the schematic they lie parallel to each other, electrically these two resistors are in series. And so because these two resistors are in series, I can then write their equivalent resistance as the sum of the two resistances. So 2 ohms plus 2 ohms gives me 4 ohms. And those are the only things that I see from our original diagram. Now, when you're working these problems, quite often it's very helpful once you've discovered a couple of equivalent resistances, or maybe only one, to redraw the diagram showing the equivalencies that you've already found. So I will do that. We'll start by putting in the equivalent 4 ohm resistor that we found. And then this is still connected to this 3 ohm resistor, this 4 ohm resistor, and this 4 ohm resistor. But now I have this other 4 ohm resistor, so hopefully you can see that what I've done here, in fact I'll sort of redraw this in some ugly pink color. I've replaced these two guys with a single 4 ohm resistor, and so this resistor goes from the terminal to this junction right here. Well, you can see that where I place the new 4 ohm resistor, it goes from the terminal to this junction. So in fact, this 4 ohm resistor in orange has replaced the 3 ohm and the 1 ohm resistor in the circuit. Similarly, I have replaced the 2 ohm in series with the 2 ohm with a single 4 ohm resistor. So you can see that it goes from this junction down to here. And if you look carefully, I go from this junction down to here. And I forgot to say that this is 4 ohms. Okay, so we've simplified the circuit quite a bit by finding 2 series resistor combinations. So now if I look at the simplified circuit and try to find resistors that I can combine into an equivalent resistance, I notice that these 2 4 ohm resistances are in parallel. How do I know that? Because both resistors are connected to this node at the top and this node at the bottom. And if I have 2 resistors that are connected to the same 2 nodes, those are in parallel. So using the formula for parallel resistors, I have the equivalent resistance is going to be 4 ohms times 4 ohms over 4 ohms plus 4 ohms. And this turns out to be, if I've done my math correctly, 2 ohms. I get 16 over 8. So these parallel resistors have an equivalent resistance of 2 ohms. Well, I can't find any other resistors that are in parallel or series right now, so I'll redraw my diagram. And to do that, we'll clear up some space up here. So now when I redraw my diagram, I still have this 4 ohm resistor. It's connected to the 3 ohm resistor and the 4 ohm resistor. And I now take the 2 4 ohm resistors in parallel and replace them with a single 2 ohm resistor. And everything else is the same. Okay, are we having fun yet? So the next thing to do is look at the circuit now, and I notice that I have 2 resistors in series, the 4 ohm and the 2 ohm, and so I can replace them by an equivalent resistance, which is the sum, which would be 6 ohms. And again, we'll redraw this. So I have 4 ohms connected to 3 ohms, and also connected to 6 ohms. Okay, so I've replaced the 4 ohm and 2 ohm resistors that were in series with the 6 ohm resistor. Again, I look at my circuit and I discover now that I have a 3 ohm resistor in parallel with a 6 ohm resistor. Again, they're in parallel because they're connected between the same 2 nodes. So 3 ohms in parallel with 6 ohms will give me 3 times 6 over 3 plus 6, which turns out to be 2 ohms. So this parallel combination is 2 ohms. Okay, well, I'll redraw my circuit again. And when I do, I get a 4 ohm resistor. And now I've replaced it by this 3 ohm and the 6 ohm in parallel, which gave me 2 ohms. So I now have 2 ohms, and I still have the rest of the network, which doesn't contain any resistors. So you can see that we're starting to get close. Here we'll use this bright pink to finish up. So now I look at the network, and I have these two guys in series. And so the combination of these two guys will be 4 ohms plus 2 ohms, or 6 ohms. And I'm at the point where I can redraw my network. This is a 6 ohm resistor. And just to show that I haven't messed with this last terminal, I'll draw it in yellow. But basically, we're done. We've taken a very complicated network whose primary function in life is to be a complicated network for this sort of analysis, and reduced it to an equivalent 6 ohm resistor. So I hope you've had as much fun as I have, and we'll hopefully see you later.